This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. Great, so now we can get on to defining integrability as we see it in real analysis. So on the real line, any collection of real numbers, x0, x1 to xn, is called a partition of the closed interval AB if x0 and xk are the endpoints, and all numbers within the partition are strictly less than the following one when you follow the indexing order. So an example could be x0, x1, x2, x3, x4, x5, and note that they don't have to be the same distance apart. So x2 and x3 here are really close. We call Q a refinement of P if Q is a partition in its own right, of the same interval, with P being fully contained within Q. So Q just contains more points. So you can think about that makes sense if we just added in one more point here, that it would be, we'd be breaking the interval into finite pieces. So we can now define Darboux sums. So if we have a function mapping from A to B to R, and that's bounded on that interval, and we have a partition of the interval, we can define the lower Darboux sum by this here. So we're going to represent it by this cursive L, F for the function, P for the partition, and it's the sum from K going from 0 to n minus 1, and it's just n minus 1 so these indices work out. And it's going to be the width between each successive element of the partition times this small m subscript k, where that is the infimum of f of x, where x is in the closed interval xk to xk plus 1. So basically it just means that this is the width of the interval, and this is the lowest height that the function achieves on that interval. And the upper Darboux sum is given in a similar way, where we just change the small m to a big M and the infimum to a supremum, so that this is just going to be the biggest height that f attains on that interval. So I've drawn it out here for just some function f. We have x0 up to x6. So here, this is the lowest part that f attains from 0 to 1. And the first term then would be the area of this rectangle. So it's the width by this height. Similarly, we have x1 to x2. It's the width, x2 minus x1, times the lowest height that it achieves. So it's the area of this rectangle. And the entire lower Darboux sum will give the area of the sum of all of these rectangles. And similarly, for the upper Darboux sum, but just now we're taking the highest point that f attains at those on the interval. So you can kind of see how we're getting towards the idea of integration. These two sums, upper and lower, provide rough estimates at the moment for the area under the curve. So if we have any function, again bounded from mapping AB to R, and we have P and Q both partitions of the same interval, with Q a refinement of P, so that's just, again, there's just more points, then the lower Darboux sum of the refinement is greater than the lower Darboux sum of the original, but the reverse is true for upper Darboux sums. And that kind of makes sense when you draw it out. Here we have the lower Darboux sum with just the partition x0, x1. So this is going to be quite a low resolution approximation, if you'd like. And it's just this, the area of this rectangle here. But if we have a refinement, that means we're going to keep these 2 points here, just add one more in the middle. Now the lower Darboux sum is going to be the sum of these two rectangles here, and that's clearly greater than just this one. And for the upper W sum, for this sort of low resolution partition P, we have the upper W sum would be the area of this rectangle, but for the more refined version, the area will be less than that because we're adding in this point here in the middle, and we're getting two rectangles, this one which is smaller than this greater rectangle. And you might be able to see here that the idea that we're approaching is that hopefully these two quantities get closer and closer to each other as we take finer and finer partitions. Great. So now we can formalize that idea I was talking about taking finer and finer partitions until the lower and upper W sums converge. So we're just going to define these two quantities, L of f and U of f, as the supremum and the infimum, respectively, of the lower and upper W sums over all possible partitions of the interval. So the idea is that we're going to take essentially the finest possible partition of A, B, or just fine enough until the supremums, until we reach the like highest possible one. This is because, as we saw earlier, when we take finer and finer partitions of the lower sum, we increase, and not necessarily strictly. So we can reach a maximum in theory, but we just write supremum in case there's some limiting process. And the same for the infimum. The finer partitions of the upper sum that we take, the smaller that the total gets. So if these two quantities are the same, essentially if the finer you get on a partition, the lower sum and upper sum both converge to the same quantity, then we say that f is integrable. Technically, this is a definition for Riemann integrable on the interval a, b, and we write this. So the integral from a to b of f of x dx is equal to either of these quantities because they should be the same. So basic example is if f of x is the constant function on the interval, we can take a generic partition P, and no matter which k we're on, those quantities from before, small mk, big mk, they're both going to be c, because the highest and lowest point that f can attain on any of those subintervals of a partition will just be the value c, because it's just c everywhere. And from that you can see that the lower and upper sums, that definitions will align. And from that you'll actually be able to see that the quantities LF and UF, they should be the same as well, because this is actually, this works regardless of the partition of P. We can see that here, because this could be the upper sum or lower sum, because as I say, they're the same. And regardless of what the partition actually ends up being, every term cancels out except for the first and last terms, so the xn and the x naught, which is just, of course, b and a. So this, we call it the lower sum, ends up being the same as LF, which is the same as UF, and it's just what you'd expect, C of b minus a, the area of this rectangle here. That's the height and the width. Also, it's just the integral from a to b of the constant C. Here's a function that's not integrable. So it's going to be 1 at every rational number and 0 at every irrational number. And again, we can take any partition here, x0 to xn. So on any interval xk to xk plus 1, that's a closed interval of real numbers, there's always going to be one rational number in that interval. Because, as I said before, you can just write out the decimal expansion of the real numbers at either end, and even if they're really close, because they shouldn't be the same, because that's what we've said here, then none of these are the same. Eventually, after a certain amount of decimal points, they'll not be equal anymore because they have to be different. So that means that you can truncate your rational number there, and you've gotten a number in between them. So that means that there's a rational number, but then by the same merit, between any two rational numbers, there's going to be an irrational number. Before we proved that the rationals are dense in the reals, i.e. the closure of the rationals is equal to the real numbers. So within every one of these intervals, xk plus 1 to xk, or flip that, there's always going to be an irrational number. So that means that the smallest value that f of x will take on any of those subintervals, so the infimum, this value mk, regardless of what the k is going to be 0, because it's always going to have some irrational number in there. So it's always going to evaluate to 0. And the supremum, the highest value it's going to take, is going to be 1, because there's always going to be some rational in there as well. So you can fill in mk equals 0 into the formula for the lower sum, and you'll see that the lower sum reaches 0, no matter what the partition is. This is just a generic partition, meaning that this quantity LF is just going to be 0. The upper sum for a given partition is given by this, which is, because mk is 1, and, pardon me, this should just be k plus 1. I was getting ahead of myself to k, but of course this will just end up being 1 times x naught, xn minus x naught, or just b minus a, which, because b and a are not equal, right? We're assuming that they're not equal, then this should be non-zero. Now this, of course, this ends up being not dependent at all on the choice of partition. So that means that UF is b minus a, which is not equal to 0, which is what LF was. So UF is not equal to BF, so this is not integrable. And it sort of makes sense if you just kind of imagine this as all the rationals at 1, all the irrationals at 0, trying to find the area under that. It doesn't have like a smooth transition from the rational to immediately afterwards that there would be an irrational. It would go down, which immediately after that there would be a rational again. And then of course be like these tiny little infinitesimal distances, but it doesn't, smoothly go down from 1 to 0, out of rational to irrational, and it's smoothly go back up. There's not really a way to calculate the area. It just jumps up and down the whole time. So there's no real sense of like what area could mean in that sense. So it makes sense that we can't find the area under this, at least with Riemann integration. Now this theorem here should be fairly obvious. The quantity LF should always be less than or equal to the quantity UF. Equal in the case where it's Riemann integrable, otherwise it should just be less than it, because it should make sense that the highest possible one of these is still less than the lowest possible one of these by the definitions of both MKs. So there is an equivalent definition of being integrable without having to consider the supremum and the infimum. You can just look at the Darboux upper and lower sums. So a bounded function on an interval is integrable if and only if, for any given epsilon, there exists a partition of the interval P such that the upper sum on P less the lower sum on P is less than the epsilon. So essentially what that's saying is no matter how small epsilon's getting, we can always ensure that we always find some partition that works. There's some like fine enough gradient whereby if we look at the upper and lower sums on that they're going to align or be close enough. They're going to be within that epsilon. So this should be a fairly intuitive idea, because this being true will mean that sort of in the limiting process, we get finer and finer p's, you know, the sup and the int, then we should get these quantities becoming equal. So an example of this, we showed that on the interval 0 to 1, that the function f of x equals x, so just the identity, right, the linear map, that is integrable. So we're going to take this choice of partition, Pn, which is defined as 0, 1 over n, 2 over n, all the way up to 1. So for p is 1, that's just 0, 1. P is 2, 0, a half, 1. P is 3, 0, a third, 2/3, 1. And you can kind of see the pattern forming there. So each one of these partitions, they're not necessarily refinements of each other because, for example, P3 doesn't contain the point a half, so it's not necessarily a refinement of P2, but they're still sort of better partitions, if you'd like, as n increases, because we're getting more and more points in between 0 and 1. So because it's a linear map, it's strictly increasing. If you were to graph it, you just have a line, so at any point xk, xk plus 1, well, the lowest point, the infimum, that the function evaluates to, on its line is just going to be xk, and the highest point is going to be xk plus 1. So that's what we get, that small m is xk, big M is xk plus 1, and xk just has the form k over n, because when k is 0, that's just 0, k is 1, so on and so forth. So we can look at the difference now between the upper and lower Darboux sums, and we just write out the definitions here, subbing in big M here and small m here, which we know are just xk plus 1 and xk, and we can bring these together and factorize it a bit to get this form here, which is just this quantity squared. And we can sub in what xk is. It's going to be xk plus, so it's going to be k plus 1 over n minus k over n, all to be squared. Then we can simplify that to be the sum of 1 over n squared. That's just going to be n copies of this, so just n over n squared. And cancelled, we get 1 over n. And that means for any epsilon greater than 0, we can just eventually find some high enough n, so such that 1 over n is less than epsilon. But epsilon is tiny, we just use a massive n, and eventually 1 over n will be less than that epsilon. So that means that this difference here will eventually get less than an epsilon. We just have to choose n to be probably pretty large, so then it'll work out. And that sort of makes sense as well, that we'd take these upper sums here, and then the lower sums would be here to be 0, here to be this box there, and the upper sums would be these ones. And we just add more and more points, and we sort of get this sort of pattern here where, if you imagine that this lower one is the lower sum, upper one is the upper sum, and as we add more and more points in between them, these will sort of shrink down to be within an epsilon of each other, with these areas underneath here. Because more and more points will just mean that this sort of zigzag will get, the space between them should get very small. Great, so that is the proof that the density is integrable, which you probably know from calculus that it is. And you can play this game with other more complicated functions. So now we'll move on to the idea of integration in RD. So in the most fundamental case, it's very similar. We just take the direct product of D intervals, so AB1, A1, B1, up to AD, BD. If that's a continuous function of those intervals mapping to R, then we can take G as this function here. So it's just going to be x1 to xd minus 1, so we just lost one dimension. And it's given here by just the, you just integrate out the final component between the bounds of that interval. And it says that if f is continuous, then this function g is continuous, which lets us set up this multi-integral here, which is well defined, because we just keep getting more and more continuous functions, so we can just keep integrating them one dimension at a time. And that means that this here is well defined, so we can just do the integral with respect to xd between AD and BD, all the way down to x1 between A1 and B1. And actually, because f will be continuous, it doesn't matter what order we integrate them in. So you can see that shown here, and this is also kind of linked back in the Darboux sums. If we just took f from 0, 1 across AB to R as being the very easy map, x, y being mapped to x times y, well, I'll just show here that it doesn't actually matter which way we integrate this. So we just take this integral here with respect to y between a and b. Well, we can just write in what f of x, y is, such as x times y. This is a continuous function in x, as we see here. X can come out, and we have a function, so the integral between a and b of y dy. We know if we take the same Pn from before, the same partitions from the last example, we can see that these actually are equal. And this is what that integral equals. You should be familiar with that. This is just plugging that in to your regular calculus methods. And we just get x times this quantity. Now we can bring this quantity here inside this new integral between 0 and 1 dx. And again, this is just a constant. It can come out to the front. So it's just this integral with respect to x dx. And again, you can kind of see why the idea of pulling the constant out to the front. If you were to look back to the upper and lower sums, if you had a constant times the entire function, like we do here, then the small m and the big M are just both scaled by that constant, so you can factor them both out, and the upper and lower sum should still be the same, so that's why we can bring these constants out. And now it's just the integral between 0 and 1, and here it's the same idea, but now b is 1 to a 0, which is the quantity here is just 1, so we just get b squared minus a squared over 4. So that's what this left-hand side would equal. Now we can do it the other way. I'll just run through that here, plug it in. It's actually a function that's continuous in y. We just sub in what we already know for the integral with respect to x, which is just 1 over 2. So we just get y over 2. Again, just a constant, so we can bring it out when we do the outer integral here. And we know what this is from before, b squared minus a squared over 2 times a half from before, and it's the same quantity no matter which way you do it. So we can look at an example of where you can't change the order. So for example, this function here, f mapping from R2 to R, this is unbounded. You can plot this Mathematica or Symbolab or something if you want to see, but essentially we get big spikes going up to positive and negative infinity. So it's x times y, and then x squared minus y squared, all divided by x squared plus y squared to be cubed when it's non-zero, and 0 when we're at the origin. So here the order in which we're integrating does matter because this is an unbounded function. So if we look at the integral First, with the function with respect to y, we just make the u substitution of x squared plus y squared equals u. So then dy is du over 2y, so this y here will cancel this y here. And we can get that this x squared minus y squared is u minus 2 times u minus x squared. So we sub that all in. We tidy it up. The 2's here will cancel. And we keep a 2 in the bottom there. A u term cancels as well. And we integrate this as you normally would. Sub in your two values here. Here, since we have u as our limit, so u as our substitution, with x, our limits change to include x, which is perfectly fine. And we get this function in x here as the outcome for this first integral. Because again, this integral, we can just do it in terms of y and hold x. Now we just do the integral in terms of x, make this u sub or v sub in this case. We work it out, we get an eighth. And then the same ideas will let you do the function with respect to x first. And we get this, which is the same as what we had before, but we picked up a minus sign and we change x to y. And you'll see why this will be different, because when we integrate that, well, we've done it before here, and we'll get now minus an eighth. So if we do it in this order, we get an eighth, and this order we get minus an eighth. So you can't just swap freely if the conditions are not met.